Hello everyone. So today we are going to talk about decision trees in Scikit-learn, and we'll be seeing the prerequisites, introduction to decision tree, sample code, and advantages and disadvantages. So the prerequisites are Python and the decision tree algorithm. So Python is a must for all the videos, especially because we are dealing with Scikit-learn library and it's completely based on Python. And decision tree algorithm, if you know it, it will be very good. If not, we'll discuss it in brief in the upcoming slides. And good to know, just like all the other videos, pandas, numpy, scipy, and matplotlib. So let us begin with the introduction. So decision tree is one of the most powerful non-parametric supervised learning method, and it can be used for both classification as well as regression. That means that for classification, something like a yes or no, or somewhere you have to classify some things into a limited number of types, whereas regression is where you need a continue value, like predicting some kind of a price maybe, or a number. And decision tree, it makes predictions by learning simple decision rules, which are deduced from the data features. So like you can see a sample decision tree over here. So for example, this is a decision tree for play tennis. We'll talk about this data set and try to understand how this was built in the upcoming slides. But over here, if you see, what this decision tree tells us is that there's a feature called outlook. The boxes are the features. So if outlook is overcast, then the answer is directly yes. I mean the test variable or play tennis feature. So that basically means the person will play tennis, is what it means over here. Yes. So if the outlook is sunny, then there is no specific yes or no just over that. So we have to look at more features. We have to branch it out even more. So if the outlook is sunny and the humidity is high, then the person will not play tennis, hence no. But if the outlook is sunny and humidity is normal, then again the answer is yes. So it uses if then conditions, and based on the data it forms a tree. So again over here, if you see if outlook is rainy and wind is strong, then the answer is no. If outlook is rainy and wind is weak, then the feature predicts yes. So this is an example of decision tree, and there are different types of decision trees. So ID3, which was developed by Ross Quinlan in 1986, and the main goal of this algorithm is to find categorical features which provides highest information gain at every node. So again, there is a formula for information gain in which entropy is used. We'll see that in the next slide. And C4.5. So it is a successor of ID3, and it converts the trained ID3 tree into sets of if-then rules. Now what is additional over here is it removes the restriction of categorical features. ID3 is mainly for categorical features, and C4.5 removes that restriction. Now C5.0, it is similar to C4.5, but it uses lesser memory and builds smaller rule sets. So it makes smaller rules basically and is more accurate, of course. So C5.0 was that, and CART or CART. It generates binary splits by using the features and threshold, which yield the largest information gain at each node. So this uses Gini index. So what this does is binary splits. You can see like there's just two split at every node. So it uses the Gini index and then it does the split. So you can read about this later on. And like I said, we'll talk in brief about ID3 decision tree. So entropy, the formula is this. So where P is the number of, in our example which we took, play tennis, P can be the number of yes and N can be the number of no. So for every feature, you have to, for every feature's, value, you have to calculate the entropy. And this is the formula for it. And then for information gain, the information gain is for a feature. So for a feature, the information gain is entropy minus the total entropy, where there is total number of yes and total number of no. You can use that to get this entropy. So total entropy minus summation of uh, all the entropies and the total number of values is present in that. So a of I over there upon the total values, I mean the total rows in the data set, the rows for that specific feature and the total values. So that is, and multiplied by the entropy of that feature. So when you go ahead and sum it up, you have to subtract it from the total entropy and you will get the information gain. So I'll just show one small example before going to the sample code, and you will understand how the tree was made. Right, so this is the data set for the tree which was shown in the PPT, and this was the tree basically, and I'll just show it to you how it was formed. So firstly, what you have to do is this is the feature that we are predicting, play tennis, and its value can be either yes or no. So now firstly we have to count how many numbers of yes are there and how many numbers of no are there. So we got 1, 2, 3, 4 and 5. So there's 5 no, or you can just write it as 5 minus, and we'll have around 9 plus 1, 2, 3, 4, 5, 6, 7, 8 and 9. So we have 9 yes, or we can write it as 9 plus. So for this whole table we have 9 yes and 5 no's. So now we can calculate our entropy for the whole table, and entropy would be, so our formula, if we see, so I've pasted the formula over here, and if you see for entropy we have minus p upon p plus n. So over here p is for positive, let's say, so it will be 9 upon 9 and 5, the total is 14. So the yes values upon the total number of rows and multiplied by log 2, again the same number, same fraction, and we have to again subtract n, which was 5 for us for the total table. The total rows remain the same, of course, and multiplied by log 2 and 5 by 14. So this is how we will get the entropy for the total table, and if you do the calculation you will get it as 0.940. So we won't spend our time doing these calculations, calculating the log value. Just take a calculator and do it, and you will get a value of 0.940. So that was our entropy for the table. Now what you have to do is you have to calculate the entropy for each attribute. So let's take Outlook first. Now if you see Outlook, so for Outlook there are three possible values. There's sunny, there's overcast, and there's rainy. So these are the only three possible for Outlook in this table: sunny, rainy, and overcast. I'm just writing their first letter. Now if you see, so with sunny there will be three no value and two yes value. See, one no over here, two no over here, three no over here, one yes and two yes. So like I said, for sunny you'll have 2 plus and 3 no's. So similarly for rainy you will have 3 yes and 2 no, and for overcast you will have 4 yes and 0 no. So just logically thinking over here, when the outlook is overcast, play tennis is yes, because there's no option else, because there's nowhere where the outlook is overcast that play tennis is no. So that's how logically you can directly understand this branch over here where outlook is overcast and you get a yes directly. But now again, to do it using the formula, if we calculate the entropy here, we'll get entropy as 0.971 for this, 0.971 for this as well, and for this you will get an entropy as 0. So I'm skipping the calculation and you can do it if you feel like it, but these are the values that you will get. And overall we had total as this for our entropy. So now for information gain, I'll just show you the formula again. It is total entropy minus summation of A of I upon the total rows into the entropy for that specific value of the feature. So now for calculating gain, I'll just write G over here, say G1. So the total entropy was 0.940, and you'll do minus, so minus 5 by 14 into 0.971. Now 5, because there's a total of 5 rows over here for outlook equals to sunny. So 5 into the entropy of that specific value for the feature is what I said. So that's why 5 by 14 into 0.971. I'll just write it below this again, minus, again we'll have 5 by 14 into 0.971. So for this as well, if you see, the sum over here is 5 and the entropy is 0.971, and again now minus, it will be 4 by 14 into 0, so this will become 0 completely, and you will get the information gain as 0.247 if you do the calculation. So similarly, we just calculated the information gain for one feature, that is outlook, and if you see, our dataset has 3 more features: temperature, humidity and windy. So similarly you have to calculate the information gain for temperature. For temperature you will get the information gain as I don't know, but it'll be lesser than this because outlook is our first node. For windy, the information gain is around 0.048. I've already calculated it. You can just cross check it. For humidity, it is 0.151, and for temperature, yes, for temperature it was 0.029. So if you see, again, the highest information gain was for outlook, which is 0.247. So that is why outlook is our first node. So our first node becomes outlook. Now you just split it into 3 because it has 3 possible values, which is sunny, overcast and rainy. So now what happens is you repeat this process, but next time when you are calculating, now you have to first, your total number of rows will be different. Now it won't be 14 because now you have to check the total number of rows for outlook equals to sunny. Then over here you will get a split. Then you'll have to check total number of rows for outlook equals to overcast. Similarly for outlook equals to rainy. So for each node, similarly you have to calculate the entropy and information gain for each feature again, and whichever feature provides the highest information gain at that point, you have to use that to, as the node over there. So that is how you build a decision tree, and in the end you will come up with something like this. And it is also possible that sometimes not all the features may be included. So like in this, if you see, temperature is not included. So if you see, only outlook, humidity and windy is there. So that means that these three features are enough to decide the outcome or the the target feature. So these three in itself make a complete decision tree, and you get a perfect, not a perfect, but then a decisive outcome from the decision tree just using these three. So that was about decision tree. And before moving on to the code, we'll see some documentation. So to see the documentation, you can just go to Scikit-learn's official website, and you can just check for decision trees. So now again, we talked about decision trees, and we talked about it being used for classification and as well as regression. Then similarly, we talked about all the types, and then there's more to it. So there's a lot of things in this, and you can explore it in your free time. So we can move ahead with the code now. So I'll just write a text saying decision tree, and we'll begin with the code. Now we're going to import pandas as pd and numpy as np, and now we have to take a data set. So over here I have downloaded a data set from Kaggle, and it's called as bill authentication.csv. So you can search it out on Kaggle and you can download it. I'll also be providing the link for the dataset. And you can use any other dataset basically, but this is the one I'm using, and it's taken from Kaggle. So you have to upload it. Once you download it, you have to upload it to Google Colab if you're using it, and you can use this icon over here to upload, and it will be uploaded like this as shown. And then you can just copy path, and we'll paste it in this command. So dataset equals to pd.read csv, since this is a csv file, and now I have to paste the path over here. So I've pasted the path, and that should read the dataset. Now we will just print the shape, dataset.shape, and we'll also print the first few rows like always. Head. So the shape is it has 1372 rows and 5 columns. So you can see the columns over here. There's variance, there's skewness, there's kurtosis, entropy, and class. So class seems to be our target variable, where you have to classify it into 0 and 1. So there's all zeros in the first 5 columns over here, first 5 rows over here, and we'll just distribute it into x and y, where x is our variance to entropy and y would be our target feature, that is class. So x equals to dataset.drop class, and axis equals to 1. So we are dropping the class because this feature, the class feature, should not be in our training data set, and it is for testing, and it is for prediction basically. So that is our target feature, what I was trying to say, and that will be our y. So y will just be data set and class. So I think it will be, yes, so that's working. Now we have to split our data into train and test. So from Sklearn dot model underscore selection, we'll import train test split. put the split and put it into variables. So x train, x test, y train, y test equals to train test split. We have x, y, and we have to give the test size. So the test size we can give it as maybe 0.2, that is 20% will be for testing and 80% for training. So let us see if we have errors so far. No errors, we can proceed. Now we won't have to do any pre-processing here. Decision tree does not require normalization and scaling. So as of now we won't do any pre-processing, but it depends upon dataset to dataset wherever required. So we'll just train our model. So from Sklearn dot tree import decision tree classifier, and we'll just take a new variable, classifier equals to decision tree classifier. Now we'll fit the model, classifier dot fit, and we have x train and y train. So now we are fitting it into the model, and we'll make our predictions into a new variable, ypred. So classifier dot predict. So we have to predict it on x underscore test. So let us see. Yes, it is fine so far. Now our prediction is done, and we can of course view the prediction by just printing this variable. But by viewing the prediction you won't understand much because you don't know the actual class. So we can just import metrics, and we can see we can see the confusion matrix, and we'll understand. So from sklearn dot metrics we'll import classification report and application report and confusion matrix. Now we print confusion matrix for y test and y pred. So y test is basically the the test data which we had and the class feature basically, and it will match our predictions with this data because that in the end should be matching if it's a good model. And we'll also print the classification report, y underscore test, and again we need y underscore pred. So you can see over here that we are getting a good accuracy actually. So this confusion matrix over here is hard to read, but like I told you in the previous videos, these two values should be minimal, and if they are minimum that means your model is working pretty good. So these two are high values, but to just make this confusion matrix more readable, what we can do is we can we can use matplotlib library. So we'll import matplotlib dot pyplot as plt, and from sklearn we'll just import metrics. So we need confusion matrix over here. Now again let's say confusion matrix equals to matrix dot confusion underscore matrix, and we take y test and y pred. Now we'll take another variable. Let's say CM display, that is confusion matrix display, equals to matrix dot confusion matrix display, and I'll just change this name over here to CM to avoid any confusion. Now over here confusion underscore matrix equals to CM, and display underscore labels equals to, let's say, false and true. So I think that should do it. Okay, we have one extra bracket over here. Now CM underscore display dot plot. So we're just going to plot it and we'll see the plot. So plt dot show. So it's small y, and there you go. So you can see the confusion matrix, and it is very much more readable over here. So there is also labels over here, which is a true label and predicted label. So when true label is false and predicted label is also false, there are 147 such values. And when true label is true and predicted label is true, that is true positive, so those are 124. So only the times when this tree has made some false predictions are these four times 3 plus 1. So like you can see, it is giving you very good accuracy and precision around 99%. So that is how powerful decision tree is, and we'll go ahead and see the advantages and disadvantages. So for advantages, it does not require normalization or scaling of data, like I mentioned during the code. It is not sensitive to missing values, so that is again a good thing. So it is easy to understand. So if you see the tree and if any data is given to you, based on that visualization of the tree, even you can make the prediction. So it is really easy to understand as to what is going on, how it is making prediction, and it requires less pre-processing or minimal pre-processing. Even in the example which we saw, we did not do any pre-processing, but we got an accuracy of 99%. So which is, really amazing. And the disadvantages. So a small change in the data can cause a large change in the structure of the decision tree, which can cause instability. Now, for example, when you saw there was a feature where there were only 4 yes and 0 no. Now, if you change that, if you make it something like 2 yes and 2 no, so by just changing 2 rows, the whole decision tree will change, because that probably feature might not be the one with highest information gain at that point. So by change of even small change in data, just changing of one value of one feature can change the entire decision tree, so that which can cause instability. Now it often requires higher time to train the model. Now the model which we trained right now had only around 1300 or something rows, so which is actually a pretty less number when you compare it with real life data sets and the real life requirements. So as compared to other algorithms, this model requires a bit more time to train, and it is not best suitable for regression. Now even though decision tree can is suitable, I mean can do regression, it can make predictions on a continuous variable, however it is not best suitable over there. Now this again depends from data to data, and for some data set it might be a really great prediction from the decision trees, but usually it's not a best suitable for regression and is better for classification. So that is it from this video, and I'll see you in the next video. Thank you.